In our previous lessons, we've been talking how we can graph linear equations. And typically that meant taking our equation and putting it into slope-intercept form. So as we look here in number 1, this is not slope-intercept form. In order to make the equation into slope-intercept form, we have to undo the equation to get y alone. So we're solving for y. So our first step to work on getting y alone would be subtracting 3x from each side of the equation. Therefore, negative 5y equals negative 15 minus 3x. Then we have to undo the multiplication of negative 5 by dividing every single term in the equation by negative 5. That would leave us with y equals 3 plus 3/5 x. Be careful, remember, a negative divided by a negative is a positive. That's why this is a positive 3, and that's why we have a positive 3/5 x. So if we're going to be graphing this equation, what we need to find is our y-intercept, the starting point of our line, and the slope, the rate of change, how we're moving from one point to the next. And we know both of those are visible in our equations. So our y-intercept comes from the constant value here, and so we know our y-intercept is at 0, 3. From that point, we're going to move according to our slope. And our slope is our coefficient here of x, 3/5, meaning we're going up 3 units and to the right 5 every single time to get from point to point on our graph. So we're going to plot our y-intercept here at 0, 3, and from that point, we're now going to go up 3 units and to the right 5 to generate another point until we run out of space on our graph. Then we always can go back to the y-intercept and reverse the slope to get more points on the other side. So we can go down 3 and to the left 5 to generate points on this part of the graph. So here I've generated my points from the starting point, up 3 and to the right 5, and then to get the points to the left of it, down 3 to the left 5. And we know for any input we put into our equation, we'll get an output, so it's continuous. We're going to connect the points to form our line. Now, as we look at our line, we see another key feature is present. We not only have a y-intercept, but we also have an x-intercept. And that x-intercept is at negative 5, 0. So, when we're graphing lines in slope-intercept form, we needed the y-intercept and we needed the slope to generate more points to form the line. Well, how many points technically do you need to create a line? If you remember from previous lessons, you only need 2 points to generate the line. Well, we know how to find the y-intercept when the input is 0, and we know how to find the x-intercept when the output is 0. So instead of always taking an equation and putting it to slope-intercept form, what if we just found the x-intercept and the y-intercept? We could then graph our line as well. So again, remember the x-intercept has the output of 0, so I could put 0 in for the output, our y, and solve and find the x value that goes with it, and that's 1 point on our graph. And we know the y-intercept has an input of 0, so we could put 0 in for x and solve for y to see what goes with it for the coordinate for the y-intercept. So if we wanted to do that by substituting in the values that we talked about, we would get the following. So again, to find the x-intercept, the output of 0, so we're putting 0 in for y and working it out and solving for x. So we know negative 5 times 0 is 0, which leaves you with 3x equals negative 15. Undo the multiplication of 3 by dividing by 3, therefore x equals negative 5. So we have our x-intercept at negative 5, 0. Again, to solve for the y-intercept, you're putting an input of 0, so 0 is going in for x. We know 3 times 0 is 0, which leaves us with a negative 5y equals negative 15. Undo the multiplication of negative 5 by dividing each side by negative 5, where y equals 3. So our y-intercept is at 0, 3. Using those 2 points, we can connect them to form our line, and notice how it matches the same line that we had when we put the equation into slope-intercept form. By finding the x and y intercepts, those 2 key features of your line, you could think that it's graphing a lot faster than perhaps putting the equation into slope-intercept form, finding the y-intercept, and using the slope to create your line. This is just another option for you when you're graphing your linear equations. Whether you want to put the equation in slope-intercept form or find the x and y intercepts, we'll still end up with the same line. So again, when we're finding the x and y-intercepts, the equation is referred to as standard form, where x and y are on the same side of the equal sign and it equals the constant. What we did was find the x-intercept by substituting 0 in for the output for y and solve for the value of x. Notice when we did that, what we were doing is taking the constant divided by that leading coefficient for x, which was a. And then for the y-intercept, we know the input is 0, so we put 0 in for x and solve for y. And the operations we did there was like taking the constant dividing by the coefficient for y. So let's see how you do graphing your lines, whether you'd like to continue using slope-intercept form or finding the x and y-intercepts. So here's an equation, 4x plus 6y equals 12. Could we graph its line? So if you wanted to put it into slope-intercept form, you would subtract 4x from each side of the equation, leaving you with 6y equals 12 minus 4x. Then you would divide every single term by 6, which leaves you with y equals 2 minus 2/3 x. Remember, always simplify each term. That's important because we now know the rate of change. We know that our slope, our rate of change, is negative 2/3, meaning you're going down 2 units and to the right 3 to generate each new point on your line. Our y-intercept, where we started from, is at the coordinates 0, 2. So now we know where we're starting. Now we know how we're moving from point to point. We can very easily generate our line. So we have our y-intercept at 0, 2. From there, we're going to go down 2 units and to the right 3 units to generate our next point. And again, we can repeat, going down 2 and to the right 3, and we could get another point in the same direction, down 2 and to the right 3, and so on. You also could go back to the y-intercept and reverse it, find points to the left of it by going up 2 units and to the left 3. So regardless how you're doing that, we can generate enough points to get our line. And then all you have to do is connect them. Now, if you wanted to find the x-intercept and y-intercept, that is fine as well. Remember, to get the x-intercept, you're substituting 0 for the output, the y, and to get the y-intercept, you're substituting 0 in for the input to solve for the y value that you need. So again, if you did your substitutions correctly, to find the x-intercept, substituting in for y, solving for x, you get a value of 3. And then for the y-intercept, substituting 0 in for x, and solving for y, you get a y value of 2. Again, notice we solved for that in our slope-intercept form, and we also saw that we had an x-intercept of 3. So again, we have the same points with the same equation, whether we find the x and y-intercepts or use the slope-intercept form. Now, what if we have an equation that looks like this? Graph y minus 1 equals 3 times the quantity x minus 4. We know that this is not in slope-intercept form, and we could put it into slope-intercept form like we've done previously, but we know there's several steps involved in that. We could find the x and y-intercepts as well, but again, there would be more steps involved in that. So is there another way that we could graph this line? So remember, this line already tells us the slope and a point that belongs on it. This is what's known as your point-slope form. Your slope is here, the number in front of the parentheses. That's representing your rate of change from point to point on your line. The point that's given to you comes from the x and y value in the second positions of the equations. Now remember, in standard form, it's always x minus and y minus. So we said before, x minus, this number here is the opposite of what you think. So you might be inclined to say it's negative, but it's positive. Okay, you might think this is negative, but it's positive. If there was an x plus, that means there had to be a negative number here to change that to an addition sign. So keep that in mind. So if we wanted to graph this equation, again, what do we know? Well, we know that the slope should be 3. And we know the other point that it's going to come from, on the line would be at 4, 1. So if we plot the point 4, 1, and we know our slope is 3, that means from this point, we're going to go up 3 units into the right 1 and put a new point. Up 3 units into the right 1, put a new point. Up 3 into the right 1, put a new point. We can go back to that reference point of 4, 1 and reverse the slope to get points to the left of it. So we're going to go down 3 into the left 1, and so on until we run out of space on our graph. And we know that linear equations are continuous, so we're going to connect the points accordingly. So here is the line that goes with the equation y minus 1 equals 3 times the quantity x minus 4. So let's try this equation. Graph y plus 2 equals 1/3 times the quantity x minus 5. So let's think about, what does this equation tell us? This equation is in point-slope form, so we should know the slope and a point that belongs on the line. Well, we know the slope comes from this value here, and that's 1/3. So we know we're going up 1 and to the right 3 from point to point on our line. What's the reference point that they gave us to start with? Remember, that's going to come from here and here. So we know our point should be at 5, -2. Because remember, the standard form uses minuses, so in order to make that a plus, that would have to be a negative value. So let's plot our starting point at 5, -2, and let's move according to our slope. Up 1 and to the right 3, up 1 and to the right 3, that's off my graph, so go back, go down 1 to the left 3, down 1 to the left 3, and so on and so forth. So then we just need to connect our points. And that blue point shifted, so we have to move it over a little bit. There we go. Connect your points. And there's your line for the graph. Y plus 2 equals 1/3 times the quantity x minus 5. All right, let's have you try this one. Graph y minus 6 equals -3/4 times the quantity x plus 2. What does this equation tell us about the graph? Well, first we know our slope was being -3/4. That means we're going down 3 units and to the right 4 units to generate each new point on our graph. What point do we have as a reference for our graph? Well, remember, that's going to come from here and here. So because it's a plus, remember this should be a -2, 6. So let's plot the point -2, 6 to start. And let's use our slope of -3/4 to generate more points on the graph. So again, we're going down 3 units and to the right 4 units. And again, down 3 to the right 4th until you run out of space going to the right. Then you can go back to your reference point and reverse your slope. Up 3 units and to the left 4 units. So you've generated several points on your line. Remember, you need to connect them because your lines are continuous. And then after we graph our lines, we could always go back to our previous objectives asking you, do you know your x-intercept? Do you know your y-intercept? Can you talk about the domain, range, and so on? Let's take a look at a couple more. We could also use graphs to solve your linear equations. So here we have y equals 2x minus 5. We should be able to graph that fairly easily because the equation is already in slope-intercept form. So we know that we're starting at our y-intercept at 0, -5, and our slope is 2, meaning we're going up 2 and to the right 1 to generate each new point on our line. So let's start there. We're going to plot our y-intercept at 0, -5, and from there we're going to go up 2 into the right 1 to generate the points on our graph. And again, if you want points to the left of your y-intercept, reverse your slope. Go down 2 into the left 1. Again, lines are continuous, so you want to connect those points. So here's our function, y equals 2x minus 5. Now we want to use it to find the solution to the equation 2x minus 5 equals 7. Well, let's see. We already have 2x minus 5 graphed, and we know 7 is an output to the function. Outputs are the y values. So that's saying you have an output of 7. So I'm going to go to the output section where 7 is, and it could be anywhere on the graph where it has an output of 7. So let's draw where 7 is as an output on the graph. Well, notice, where do they intersect? Right here. What input goes with that? Well, if we go down to our inputs, we can see that the input that goes with it is 6. So we've solved our equation graphically. We know when there's an output of 7, the input is 6. Now, algebraically, you know how to solve that by adding 5 to each side and dividing by 2. But if you have the graph, it's very easy, looking like we did before with our functions. If you know the output, what input goes with it? Let's try another. So here we're going to graph y minus 1 equals 1/2 times the quantity x minus 6. Well, what do we know about this equation? This equation is in point-slope form. So the point that we're working with is 6, 1. The slope is 1/2. So let's plot our point 6, 1. And from there, we're going to go up 1 and to the right 2 to generate points. Now, we can go back to the reference point and go down 1 and to the left 2 to generate more points for our line. Again, lines are continuous, so you want to connect those points. So there's our function. Now, we want to find the solution to the following equation. 1/2 times x minus 6 plus 1 is equal to -4. Well, what does this mean for us? Well, we have the graph of the function here on the left. And notice it's just a slight variation because we had to get the output y alone, so notice we just added 1. It's still another format of the same equation that we're working with. We have an output of -4, so let's draw where -4 as an output is on our graph. And we want to see when our graph gives us an output of -4. Well, that happens here. See how they're intersecting? The input that goes with it happens to be -4. So you just solved your equation graphically. For this situation, that's a lot faster than having to distribute, combine your like terms to get x alone. So that's kind of one of the good features when you have a graph function, to use it to look at the corresponding output to find the input for some solutions to your equations. So now it's going to be your turn to practice graphing your linear equations and looking to see what kind of equation is given to you. Is it something already in slope-intercept form? Is it something that's on standard form and you just want to find the x and y intercepts quickly to create the line? Or is it in point-slope form, so you can use that to help you graph as well?